Afternoon, my name is Abraham Flores. I'm a PhD student in the Computational Science program. My advisor is Dr. Kenneth Nolan. Today I'll be giving you a brief tour of variational Monte Carlo calculations of neutron scattering from tritium. Few people have attempted to compute ab initio models of nuclear collisions. This is mostly due to the fact that it is quite computationally intensive. The vast majority of ab initio computations have been calculations of bound states, because those have the easiest boundary conditions. Having ab initio models of nuclear properties is a major goal of the field, simply meaning models starting from realistic protons and neutrons. This is still not achieved for most types of nuclei. VMC has been successful and is the starting point in more successful methods for computing bound state wave functions in nuclei lighter than carbon. VMC avoids working in a large basis of orthogonal functions by instead computing correlations between pairs of nucleons from their interaction and building those pair correlations into an elaborate guess wave function. The cost is that the integrals have to be computed by Monte Carlo methods. We start with a correlated trial wave function and optimize its parameters variationally by minimizing its energy with respect to an interaction potential that describes the two-body scattering as well as 3 and 4-body states accurately. We use the Coblaw algorithm to perform the optimization. The difference between collisions and bound state problems is the boundary condition on the wave function. Bound wave functions have to go asymptotically to zero where nucleons are far apart, but in collisions, the boundary condition matches the wave function onto a sum of incoming and outgoing waves. Before we continue on, a brief introduction to the basics of quantum scattering. We start with the source, in our case a neutron beam narrowed by a culminator, colliding with a target, in our case tritium. From there, neutrons hit the detector. The neutrons are counted within some solid angle in relation to the target. From the counts, solid angle, incident flux, and scattered flux, we are able to compute the differential cross-section and eventually compute the total cross-section. In order to use VMC to compute collisions, we restrict the location of the scattering neutron so that it stays inside a surface at a fixed 9 Fermi distance from the triton center. We use the wave function's derivative across that surface as our boundary condition. The scattering probability is a known function of the energy and the surface derivative. To generate the dependence of scattering on projectile energy, we compute separate wave functions for various boundary conditions and map out the scattering probabilities as a function of the minimized energies. This direct method works fine for single-channel collisions, that is, collisions that retain the same angular momentum quantum numbers throughout the collision. In collisions involving multiple channels, the wave function needs a separate boundary condition for each channel, and after computation it has to be decomposed into the channels because the channel amplitudes at the surface are needed to compute the scattering probabilities. That outer part of the wave function also is hard to sample well and unable to take advantage of the short-range pair correlations that are mainly responsible for the accuracy of VMC. Fear not. It can be shown that those surface amplitudes can be computed through integrals over the short distance part of the wave function where the particles all interact with each other. This avoids the pitfalls of the direct method. The integral method uses the most accurately constructed part of the variational wave function. The integrals explicitly contain the nuclear interaction potential, so we aren't just relying on the accuracy of the variational ansatz. Here we have two figures for zero total angular momentum in the p partial wave. The left figure being the part of the wave function consisting of a separate neutron and triton for a single wave function. The dotted line is the directly computed overlap. There is a neat trick that is not obvious for the integral method in our VMC framework. We have found that we can avoid generating separate wave functions at every projectile energy by adjusting a single input parameter of the integral. Each line in the left figure represents the overlap of the 4-body wave function onto the neutron-triton space with a different projectile energy. This simple scan greatly reduces both the human and computer work necessary to map out the phase shift as a function of the energy. On the right, we have a figure comparing phase shifts as a function of center of mass energy, computed from the direct and integral methods, in contrast to more developed methods. The phase shift is a convenient and widely used parameterization of scattering probability. The solid black line in the figure on the right is our empirical expectations. The solid black squares are a state-of-the-art calculation using the Alt-Grasberger-Sandhaus method with the argon V18 potential. This is our theoretical expectation. The integral method clearly shows improved accuracy in computing phase shifts. Total cross-section is directly related to the number of scattered nucleons detected. Cross-section is the physical observable that allows us to relate our theory to experiment. Here we have computed the total cross-section of neutrons scattering from tritium as a function of center of mass energy with a few nuclear potentials. For the argon V18 potential, we fall short of matching the AGS calculations. However, our results are quite remarkable when you consider that we are only using VMC wave functions. In the path ahead, the integral method will be even more important for Green's function Monte Carlo, which builds on a VMC starting point to get essentially exact wave functions. But in a random sample representation, that would be very hard to read surface amplitudes out of directly. Coupled channels may be impossible without some way to read the long-range amplitudes out of the short-range wave function. We believe that with improved wave functions, the Green's function Monte Carlo, we will be able to accurately compute the cross-sections for immensely important nuclear reactions. In summary, we have developed a method for extracting scattering information from wave functions that plays more to the strengths of our computational approach by focusing on the wave function interior. We are happy to announce that we are submitting for publication in the coming weeks. Thank you for listening. Have a great day.